Okay, hey, thanks everybody for joining us today for the algae management webinar. This is part two of a sort of four-part educational series. So if you missed our last series, we will have a link where we covered biofilm, but today we're going to be covering algae management. Very excited to be talking to you guys about these irrigation ponds today. So quick introduction to Moleaer. Moleaer is a nanobubble technology company where we develop and implement our nanobubble technology generators. We work to increase efficiency, productivity, and sustainability across a lot of different verticals. I work specifically in irrigation, so whether that is outdoor ag, row crops, ornamental production, high-tech ag, hydroponics, really all across the board. I work in that irrigation side of the business, but we do have a lot of other different sectors. You'll find the common theme that we're really helping production do more with less through our water treatment systems. Quick introduction to myself. If you haven't met me, my name is Justin Leavitt. I work for Moleaer. I've been with Moleaer for almost about 3 years now. I'm the irrigation specialist on our team. I consider myself a biological enthusiast, horticulture professional, integrated pest management and pathogen management advocate, small-time fig farmer, and a hobby greenhouse grower. So I worked in the green industry really all my life, from loading up bags of mulch into cars to working in production greenhouses to helping develop pest management and pathogen management plans, which really ultimately led me to working with Moleaer was finding alternative ways to manage pathogens. Like I said, last quarter's webinar, we covered biofilm. So biofilm is a really common issue. If you are dealing with biofilm, I recommend you check out our last quarter's webinar. It is on the Moleaer YouTube channel, but you can also Google breaking the biofilm barriers, and it should come up as well. But what we're going to cover today is algae management. We're going to talk about what is algae, why, what are the real costs of poor water quality. What does it look like when you start to sort of transition and shift into higher water quality, and what's the deliverables, right? What are we getting for our investment when it comes to improving water quality? So starting out with what is algae? Algae is a very, very broad category. If we think algae, there's usually like a very specific picture of what we have in our minds, but algae is a typically autotrophic organism that ranges from microscopic single-celled forms, but also larger multi-celled forms. So things like seaweed and kelp fit in that sort of algae category. Now, algae are really interesting. If you're a plant nerd, then you can really get into algae like I have. They are different, of course, than higher plants. They don't have true roots or stems or leaves, but they do perform photosynthesis using chlorophyll and have a lot of other sort of similarities. Now, I travel quite a lot visiting irrigation ponds, visiting a lot of different potential customers, and there's three common types of algae that I see generally across the board. We have our filamentous algae, our planktonic algae, and then blue-green algae, which is a cyanobacteria. Now, some key ways to identify algae. For your filamentous species, they look very almost hairy. They have strands. And so if you can take a stick or pull skimmer and kind of pull it out of the water and it comes up in a very sort of filamentous way or sort of almost looks like green hair strands, then often that's your filamentous algae species. All of the algae can be very disruptive. These here can be very disruptive to the pond ecosystem, but your filamentous algae is really rough on your filtration system and also pump intakes. Now, planktonic algae, or sometimes it's referred to as that pea soup algae, can be beneficial to the overall ecosystem in small amounts. But when you start to see coverage of 10 or 20% higher, this becomes very problematic for your ponds, along with blue-green algae. So blue-green algae is technically a cyanobacteria, which is harmful to animals and humans. If you've seen on the news, it seems like more and more waters are warmer, algae breaks are worse, and you might hear of a pond getting shut down or a lake getting shut down, and that's generally because of cyanobacteria. Can kill dogs and animals, also can cause a lot of issues for humans. So understanding what algae you're dealing with is going to be important to kind of look at the severity. We really don't want cyanobacteria in high amounts in our irrigation ponds, especially if we're using things like overhead irrigation, right? We don't want, no one's drinking pond water by any means, but we also don't want to be sending around cyanobacteria where it's splashing around, can be on people's hands, mouths, ears, eyes, things like that. So here's 3 common types of algae. If you're not sure what you have, feel free to reach out to Moleaer and we can help you with that. Now, why algae? Goodness, there's a lot of reasons why algae can be prevalent. Some are external factors, right? Increasing temperatures of waters, but there are also factors that we can try and manage. There's 3 kind of common denominators that I see when I have algae bloom issues, and first and foremost is nutrients. So influx of water runoff provides high levels of phosphorus and nitrogen, which can fuel algae growth. So if you're using an irrigation pond and your drainage water or your return water goes back to that pond, that is a very responsible thing to do. And I commend you for doing that, being good stewards of water and of your resources. But we do need to understand that we are also, returning a higher amount of phosphorus and nitrogen back into that water body, and we have to account for that higher level of nutrients, because those nutrients are what's fueling the algae growth. Geese as well. It's incredible the amount of ammonia and nitrogen that geese can contribute into a pond. And so when we're thinking about nutrients, of course, what can we do from a irrigation perspective, but also we need to be looking at other nutrient sources. Another reason why we see algae is organic muck buildup. This can come from leaf litter, grass, or organics essentially sinking down to that sediment layer and developing muck. One of the common contributors is algae itself. Generally in 1 or 2 fashions, we see a lot of fruiting algae. It's pretty common in the industry for people to throw out like a copper-based product and kill that algae, but the organic mass sinks down to the bottom and contributes to that organic muck. And it's also releasing that phosphorus back into the water as well, which can be just sort of problematic down the road. That muck or your sediment layer is really the petri dish or the medium for your microbial communities. And so we really want to reduce the amount of organics and have a sort of firm or harder sediment layer. And really the last contributing factor, maybe not the only, but most prevalent, is depleted oxygen. Depleted oxygen levels throughout different areas of your water column. These depleted oxygen levels can shift your microbial communities from what were maybe once aerobic to anaerobic, which can cause a lot of sort of chain reactions within the water ecology. But also the depleted oxygen levels can create an environment for weak bonds, which allow for phosphorus to fuel algae growth. So we'll talk a little bit more on a couple slides about these bonds, but it's important to just understand that algae is really aggressive on a cycle, right? It takes these nutrients that build up in the water, and then when the parameters are correct with water temperature and sunlight, you get these large algae blooms, which contribute to really big fluctuations in DO, also really big fluctuations in pH as well. That algae dies, whether through maybe an algicide or winter kills it, and then we are re-releasing these nutrients back into our pond and sinking that organic mass to contribute to the muck layer, which again reduces the level of oxygen that we have. And so this cycle here is something that we need to disrupt if we want to reduce the root causes of why we have algae. There's a couple things you can do today. Looking at nutrients. If you are returning irrigation water back to your pond, looking at things like living drainage routes, creating pathways of living plants where they can try and pull some of the phosphorus, nitrogen, and other nutrients out of the water as it's being returned is going to be helpful. Also, goose management programs. I kind of say this jokingly, but it can be serious. If you have a high geese population, then you can contribute a lot of nutrients. So one of the ways that you can sort of avoid having to break down all these nutrients is reducing that inflow. So you can have high grass around your water body, which can reduce the geese's comfortability with that water. Using things like fake coyotes is something that you can consider. Keep in mind, geese are maybe smarter than we give them credit for. If that fake coyote has been sitting by that pond for 2.5 years and hasn't moved, then the geese are going to feel very comfortable with it. So understanding that some of these things are going to be short term and might take a little bit of moving to create a sort of risk for the geese. Oh, of course. Okay, joking here, but real coyotes, introduce those at your own risk there. So managing nutrients coming in is something that you can implement today. Also, reducing the organic muck. Again, if you're returning water from a irrigation pond, if you can create sediment traps so that water is just not free flowing, carrying high amounts of organic material. Looking at your dump piles, right? If you have, organic dump piles, for example, making sure that those aren't sort of bleeding into the pond as well. Mowing grass clippings away from the pond. 3 or 4 strips of grass clippings blowing out away from the pond is going to be key. Worst thing in the world is to have freshly mowed grass and all those clippings floating in the water, releasing all the nutrients and contributing to that muck problem. Also leaves, right? I've seen a lot of people utilizing things like maple trees or oak trees where they're creating a lot of shade for the pond, reducing the water temperature, which is great. You don't necessarily need to catch every leaf. You don't need to be out there skimming it like it's a pool. But during your big leaf drops, if you have considerable piles of leaves that are near that pond, I recommend blowing those as far away as you can. That's within reason, so that they don't actually blow into that water. The water, the organics create a oxygen demand, and so of course we want to satisfy that by implementing technology that will introduce high amounts of oxygen into your water. But let's start with minimizing the needs and reducing the amount of organic muck that can build up in the first place. And then lastly, right, depleted oxygen. If you have depleted oxygen, looking at Moleaer oxygen nanobubble systems are really the way to go. We're transferring high amounts of oxygen into water, which is going to completely sort of shift the ecology of that water. There are other technologies out there. I would just be somewhat wary of simple bubbler systems or fountain aerators or even traditional aeration. I would say majority of the Moleaer equipment that I have on irrigation ponds are there replacing a previous aeration system or a bubbler or fountain system because it just wasn't aggressive enough. We need to drive high amounts of oxygen into that water, especially on irrigation ponds where we're pulling water out aggressively, returning water aggressively, we have high nutrient loading. Costs of bad water. There's a lot of costs of bad water. We don't always see it because we utilize Band-Aids all down through production to try and kind of reduce that burden. But costs of bad water, number one for me is pathogens. I do a lot of water testing, and I can tell you ponds that have lower oxygen levels, lower ORP levels, generally higher in algae counts, will also have higher bacteria and fungal CFU levels, usually have higher waterborne pathogen levels in them. And so as an industry, we work really hard to reduce pathogens. And going from IPM or integrated pathogen or pest management, We do a lot of prevention. We do preventative fungicides, right? Whether it's a foliar preventative fungicide or a foliar or sorry, a preventative soil drench for maybe the roots or the crown. And we do these preventative applications because we know that we're going to have pathogen issues if we don't. And so what I would recommend is that we take it one step further and say, listen, if we know we have high levels of pathogens that are growing in our ponds, instead of just treating at the plant level, let's try and minimize the amount of pathogen growth at the source so that we don't have to be so reliant on chemical consumable fungicides. Also filtration, high amounts of organic materials, high amounts of algae are going to cause a lot of wear and tear on filtration systems. Now, what I will say is great filtration can make a huge difference in your water on the outflow, right? You can take bad water and run it through some very nice filtration, and then out the other end you have better quality water. We've known this, we've seen good filtration. The issue though is that with filters we're treating water as it's going out the door into the plants. We're not treating water at the source. So filtration is somewhat of a ticking time bomb, because as your source problem gets worse, because if we're not treating our irrigation ponds, the algae organic loading gets higher and higher. Our filters are only getting older and older, only picking up more and more wear and tear. So it's a little bit of a perfect disaster to have your problem get worse and your solution also, get worse in a different way. And so filtration is important, but we want to treat the source so that our filters last longer and work better. And lastly, I'd say the cost of bad water boils down to plant production. Water is the #1 resource on the farm. If you don't have water, you don't have a farm. But I would ask you to look at water a little bit deeper into that and ask yourself, if it's the #1 resource on my farm, do I know if it's good quality or bad quality? Do I know if my water is getting better or worse over time? And if your water is getting better over time, there's benefits to that. That can be, reducing your oxidizer expenditures for cleaning lines, reducing labor that needs to run around and change filtration, labor that's running around checking drippers, but also, better quality water is going to give you a better quality plant. And that's hard to notice when water deteriorates over a long time span. But when you go from lower quality water to initially much higher quality water, you'll see that difference. I want to bring some data to these points here. So looking at pathogens, here's a study where we have Moleaer treated water versus the control. And on the left, these are pathogen levels in the substrate itself. You can see just with Moleaer's oxygen nanolevels being present, we have a large reduction in these pathogens from a pass or fail point of view, but also what is the severity level of these pathogens? Do we carry high amounts of pathogens where we need to rotate 4 or 5 different fungicides to get things under control? Or are we carrying very low CFU values, very low content of these pathogens, where in small amounts pathogens might be in your water, but the plant never is affected by it, or a small biological fungicide application is all that's required to manage these lower levels. Chart here on the right is a measurement of pythium in drainage water, and the comparison is the Moleaer treated water versus the control. And you can just see warm season pythium grows and grows and grows versus the nanobubble treated water where the pythium levels stayed much lower. And so I think it's really important that we treat a lot of these problems at the source. We're very used to applying lots of fungicides, which is a very labor-intensive application, but we don't need to be carrying nearly this high pathogen loading from our source water. Here's an application where a grower decided to make some changes, where they installed an oxygen nanobubble unit. Of course, the main application for them is algae, right? Let's reduce the algae. And when they reduced that algae through the treatment, they saw also a reduction in clogged drippers. They brought their water, which was about 1.5 parts per million dissolved oxygen, to consistently above 10 parts per million. And they did not need to use nearly as many inputs for pH control. And so, obviously pH control is really important because it's tied to our nutrient availability. So if you have algae, you typically have these massive swings in pH. And so if you're not controlling that, then that means you also have massive swings in your nutrient availability. So, we can always try and do maybe acid injection and things downstream to get pH in the right place. That's something I would recommend. But tackling the problem at the source would be reducing the materials that are causing these massive pH swings, which is often the algae. Here we're looking at a tree grower where, again, we significantly reduce the algae, provide them cleaner water, which is always kind of step one. And depending on the starting water quality and depending on how aggressive you want your water treated, it's somewhat dependent on how we get into step one and step two, right? So step one is always facility benefits. Can we reduce algae? Can we increase water quality, reduce stress on filtration, reduce pathogens in our source water? But after we start to satisfy the biological oxygen demands of the water, we can increase that water quality to much higher oxygen levels, which for them allow them to have better caliper, increased tree growth, increased root growth. And what we understand about root growth, roots love oxygen. They can consume incredible amounts of dissolved oxygen and help produce high amounts of root growth. And of course, what follows root growth is a root structure that can support, again, better foliar development. So for this tree farmer, they saw that better root growth, but they also saw largely increased shoot development, increased tree growth as well. So tackling your water quality is somewhat twofold. It's getting your water to a point where there's value for the facility and the equipment, but then they're stacking those sort of benefits and oxygen levels so you can deliver that out to a root zone. So generally the next question is always, well, how do I know if I have good quality water, bad quality water? How do I know if it's getting worse over time or getting better over time? And the answer to that is, well, you have to test your water. You have to test it somewhat consistently. I would recommend testing it even quarterly and keep track of that data. I personally like to look at the dissolved oxygen and ORP, or oxidation reduction potential levels of that water 4 times a year. So the way I categorize this, 5 parts per million or dissolved oxygen or less, I would consider closer to the unhealthy side of things. And then where we want significant amounts of value to be delivered is when we're consistently seeing 9 parts per million of dissolved oxygen or higher. This is what's going to give us our significant algae reduction, better root hairs on plants, reduction in low oxygen loving pathogens, and being largely more beneficial for that water ecosystem. Where you measure your water is also important. I like to take most of my measurements about 1 foot off the sediment layer. So generally what that means is you need a dissolved oxygen and ORP probe. You can typically get those as like a 2-in-1 meter, just like you would get a pH and EC meter. If you can get one with a very long cord, that's going to give you the most accurate representation. So I have one where I can sink that meter 20 or 30 feet down and get accurate measurements. In a pinch, if you have to, you can always try and sink a bucket and draw water up. That's not the best representative sample, but you can use that in a pinch. Looking at ORP, that's oxidation reduction potential. So what is the water's potential to reduce oxidation measured in millivolts? And so a lower ORP is going to be considered unhealthy. It's going to take higher amounts of oxidative, sort of chemicals to make changes, whereas a higher ORP is going to be considered healthy. Now, 200 and above is what I would consider healthy. I really want to be targeting more closer to that 250 to 350 range in an irrigation pond. That doesn't happen on its own, but when you can get it there, that's when you start to see consistency out of your dissolved oxygen levels. That's where you start to see that aerobic sediment activity, which is, aerobic sediment activity is going to be key into breaking down that organic muck. This is where we see those algae reductions and mainly a chemical and biological shift in that water. If we have, dissolved oxygen closer to 9 parts per million and we have ORPs closer to that 200, 300 range, we are going to start to see changes, biological and chemical changes in the water. From a biology perspective, it's the change of the microbial communities. Those are sort of the lifeblood of the pond and driving what is happening within that water. When we move from anaerobic to aerobic microbial communities, we start to see high levels of muck digestion, as well as the chemical reactions come from creating strong bonds. In the presence of high oxygen, you'll find that your phosphorus starts to bind with iron and sometimes can bind with manganese. It sinks down to the sediment floor, more or less creating a sort of sequestered environment where it is no longer available for the algae. And so what we want to do, getting back to the sort of nutrient cycle or the algae cycle, is we want to shift the microbial communities so that they are more aerobic, digesting muck and starting to outcompete your anaerobic microbials. And then we want to create these chemical reactions where the phosphorus is no longer in abundance, available for the algae to produce these aggressive algae blooms. So if we can limit the microbial action from an anaerobic perspective, if we can limit the food source for the algae through the chemical reactions, we can create some very positive changes for that body of water. What this generally looks like is a NEO. This is sort of our flagship our treatment unit. It can go from 50 to 250 gallons per minute, but we take a individual approach. One size does not fit all. And so, we can go up to thousands and thousands of gallons per minute treatment. And we can go lower, of course, than 50 gallons per minute. But typically, we're recirculating on an irrigation pond. And so we're pulling water out, running it through our equipment, which creates, billions of these nanobubbles and dissolved oxygen and returning it back, which gets delivered to that sediment layer. We also have the option of injecting ozone. We do oxygen quite a bit. The results and examples I've given you today was just using oxygen, but ozone can provide a really much higher level of sanitation and oxidation. So if you don't want to use an oxidative partner like a granular hydrogen peroxide, the ozone can be a good option to look at. So we install this equipment on a large range of different applications, from irrigation ponds, freshwater tanks. We can also turn these into inline injection systems where you're driving oxygen and nanobubbles inline. If you want to learn more about the nanobubbles, please check out the biofilm webinar. We talk all about the benefits of the nanobubbles there. But the treatment objectives for irrigation ponds generally look at trying to drive as much oxygen as possible to that sediment layer, increasing the ORP of your irrigation water, and really shifting the culture of your water to, instead of getting worse every year, but providing better water quality month over month, year over year. So a lot of these customers send us pictures like these within, sometimes it's a couple months, sometimes it's longer. It depends on how we aggressively want to size equipment and your starting water quality. But the goal is always, step one, create these facility benefits where we have low levels of pathogens, we have low levels of algae, good filtration. But when we can benefit these ponds and satisfy the biological oxygen demand, then we can start to get into really high levels of oxygen and deliver that to the root zone. When we can deliver that, obviously, to the root zone, we also see significant growth from a foliar perspective by giving the roots everything that they need. So this was a quick 30-minute recap webinar. Appreciate everyone joining. We got a couple key takeaways. Water testing is essential to understanding if your water is getting better or worse over time. Getting a dissolved oxygen and ORP meter is going to be very important. Making sure that you measure, about a foot off the bottom is going to also be important. Again, if you can't do that, try and bring water up to you. Key factors of algae and other water quality issues is almost always boiling down to excessive nutrients, having a high amount of organic muck, and then depleted oxygen. Those three things are issues that we want to solve so that the irrigation pond ecosystem can manage itself. Moleaer, we have proven technologies that will work on your irrigation ponds along with tanks and inline applications. So I'd love to hear some questions, but first off, this is my favorite slide here. What did the owl say at the end of the presentation? Who's got questions? All right, thanks everybody. I'm gonna exit out on my screen here and see if we can take any questions.